Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at dialysis very briefly. This comes from chapter 13 from our textbook, which is on membrane separation processes. So, there's a lot of vocabulary that is probably new to you. The first is about what it is that we are moving across the membrane. And basically what we are doing with dialysis is transporting across the membrane these small crystalloids, which are small solute molecules, and they move due to a concentration gradient. So this is purely mass transfer. Molecules are all different sizes, and some of them are going to not fit through the membrane's pore structure. And so those small insoluble molecules that cannot transport are going to be just the rest of the colloid. The feed will be called the dialysate, and the solvent that accepts the molecules is the diffusate. So it goes from the dialysate into the diffusate. This dialysis process will work best whenever the molecules in the dialysate are really different sizes. So therefore they'll diffuse at different rates and transport across the membrane with different amounts of ease. Now, the dialysis may be limited by the diffusion of the solvent across the membrane into the diffusate, which may mean that that is the only step we need to look at. But more frequently, we need to look at the diffusion at all layers. The equilibrium for our dialysis can be defined with an equilibrium distribution coefficient. And in this case, what we're looking at is C sub S and C sub L. C sub S is the concentration in the diffusing solute compared to the concentration in the bulk liquid phase. So C sub S over C sub L. That's going to be our distribution coefficient. And you would need to get that from some sort of equilibrium data set. The mass transfer really happens in three distinct steps. So first, the solute has to diffuse through the dialysate to the membrane surface. And there's probably some bulk concentration out here in the free fluid of the dialysate to what is on the membrane wall there. And we can estimate this using our convection form for mass transfer. So the mass flux is the Kc, the mass transfer coefficient, times the delta C on the dialysate side. Then we need it to diffuse across the membrane. And there will be some sort of concentration gradient across here, and this will be more like a fixed law looking thing, but basically we can just assume that that'll be fairly linear. N sub A diffusivity over L times the concentration difference across the membrane itself. And then finally it will go into the liquid phase and diffuse back out into the bulk diffusate system. And this again is Na times Kc2 times the concentration difference between the wall concentration and what's happening in the bulk diffusate fluid. Now we can combine these so that we are able to do like we did maybe in heat transfer, but using the electrical circuit analogy that each of these is a resistance. And so the reciprocal of these mass fluxes is a resistance, and we can add up the resistances to get a net resistance. And so we can find that over the entire system here, N sub A is the concentration difference from the bulk fluid in the dialysate to the bulk fluid in the diffusate, divided by the sum of resistances. These resistances are the 1 over Kc pieces, and 1 over P sub M is a grouping of diffusivity times the K, that distribution coefficient, over L, the length of or thickness of our membrane. So finally, why do people use dialysis? I mean, we've all heard of hemodialysis, but that's usually what most people just simply call dialysis. But there are many other applications. So, when you're doing cellulose processes, you usually add sodium hydroxide, and then at the end, you need to recover that. And so, dialysis can be used for that. Metals processing also is a time when you have acids that you have added to extract your material from the ore, and you want to recover that. And so dialysis can be useful there. Culture products from fermentation, or when you make cheese, the whey has various solids in there, so salts, it may have some sugars, etc., that you want to extract from the whey. You can also actually use this to reduce alcohol content in beer. You've heard of some of the like O'Doul's, the light alcohol beers. And then finally, pharmaceutical processing has many applications of dialysis. So this concludes our quick survey of some of those topics that we couldn't really address in class. I thank you very much for your time.